Greetings, space travelers. Today we explore the most extreme regions of space-time, black holes, regions where reality itself seems to break. To understand a black hole, we must first talk about limits, specifically the Schwarzschild radius. In 1916, Carl Schwarzschild calculated the critical radius where an object's gravity becomes so strong that light cannot escape. The formula is Rs equals 2gm over c squared. It tells us that the size of a black hole is directly proportional to its mass. For our Sun to become a black hole, you'd have to compress its entire mass into a sphere just 3 kilometers wide. And for the Earth, it would need to be the size of a marble, just 9 millimeters across. This critical boundary is called the event horizon. It's not a physical wall, but a point of no return. Once you cross this threshold, you are causally disconnected from the rest of the universe. No signal can ever return. Inside, space and time warp so severely that all paths lead inevitably to the center. There is no away. To a distant observer, things get even stranger. Gravitational time dilation makes an object falling in appear to slow down. They seem to freeze just outside the horizon, their light red-shifted into invisibility, though they themselves cross right through. From the falling observer's perspective, however, time flows normally until they reach the most mysterious part, the singularity. At the center lies a point of infinite density and zero volume. Here, our current laws of physics simply break. General relativity predicts that curvature becomes infinite. It's a sign that our understanding of the universe is incomplete. Modern physicists suggest quantum effects might heal this point, replacing the singularity with something less infinite. But before you reach the center, you'd face a process Stephen Hawking called spaghettification. Because gravity gets stronger with the square of distance, the pull on your feet is much harder than the pull on your head. You are literally stretched like taffy while simultaneously being squeezed inward from the sides. Interestingly, the larger the black hole, the gentler this effect is at the horizon. Mass really matters. For a supermassive black hole, you could cross the event horizon without feeling a thing, at least for a while. We can also see black holes through the way they bend light. This is called gravitational lensing. They act like giant lenses in space, creating circles of light called Einstein rings and warping our view of the cosmos. Light from the disk behind the black hole is bent 180 degrees, appearing to wrap over the top and bottom. In 2015, we detected ripples in space-time from merging black holes, the first direct proof of their existence. This discovery of gravitational waves opened a whole new way of hearing the universe. We've even seen them spaghettify stars in events known as tidal disruption events. Truly spectacular. Black holes are the ultimate tests of our theories. They are where space-time breaks and where new physics begins. Thank you for joining me on this journey into the dark. Remember, keep questioning the fabric of reality. Subscribe to James's Physics 101 for more micro lessons on the universe. See you in the next one. Goodbye for now. And stay curious.